Hey everybody, this is Pedram at PhysAcademy.com with a one-dimensional kinematic practice problem. This problem is within a complex level range for algebra-based students and a medium level for calculus-based students. The goal of this video is to work through a problem assuming you already went through the fundamentals in the lecture class. A few little notes before we go through the problem. By one-dimensional, or in short 1D, we mean all objects moving in the same direction. Okay, now let's read this practice problem together. Two bacteria are next to each other and moving in the same direction. Alright, the same direction gives us a clear clue that the problem is one-dimensional. One moves with an initial velocity of 20 microns per second, accelerating at the rate of 5 microns per second squared. Okay, it means the initial speed and the acceleration are both in the same direction and toward the positive x-axis. That means this particle, or bacteria here, will speed up over time. There is no any turning point. There is no any slowing down. It's going straight, speeding up over time. The other starts with a velocity of 60 microns per second and decelerates at the rate of 20 microns per second squared. This means the initial speed is toward the positive x-axis. Still, because the acceleration is negative, it slows down over time. Eventually, at some point that we don't know, it will stop moving and then roll back while speeding up toward the negative direction of the x-axis. We call this position a turning point, that this turning happens. First, find the time and position when the bacteria meet again for an epic battle. Second, sketch an accurate plot of the position versus time for the motion. Starting from part A, the first thing to do for a kinematic problem is to sketch our coordinate system, which is a straight line for 1D case. Let's mark the initial positions for bacteria 1 as B1 in blue and bacteria 2 as B2 in red. Then we sketch the velocity and acceleration vectors. For bacteria 1, both are positive. For bacteria 2, the velocity is positive, still its acceleration is negative. So I have this vector toward the negative direction of the x-axis. I'm going to fix the length of the bacteria 1 velocity vector. The size of the vector represents its magnitude. 20 is 1/3 of 60. Therefore, I need to have it shorter than the bacteria 2 velocity vector. Now let's write down the general equations of motion for these two bacteria. Displacement of bacteria 1 along the x-axis is equal to half of the bacteria 1 acceleration along the x-axis times the time it takes for the bacteria to meet, plus the initial velocity of bacteria 1 along the x-axis times the time that it takes for bacteria to meet again. The same is true for bacteria 2. please pay attention to subscript 2 as we are talking about bacteria 2 here. Some of the variables are the same between these two equations. Delta t, the time it takes to go from the initial point to the final position, also is the same for both of them. Delta x, the displacement along x-axis from the initial spot to the point that they meet again, is the same for both bacteria. So I rewrite these two equations without subscripts for delta x and delta t. Our goal in part A is to find delta x and delta t. And as you see here, we have them in the form of two equations, two unknowns. When we have two equations, two unknowns, the first step is to have all delta x's on the left side of the equation and delta t's on the other side. Well, lucky here, we already have the equations organized, so I don't need to worry about it. Now let's call the first equation 1 and the second one 2. So 1 is equal to 2 because the left-hand side of both of them is delta x. By doing so, we eliminated delta x and we can solve for delta t. After a few lines of reorganizing variables and canceling a bunch of them, we get to this equation for delta t. Now let's plug in our values. Be careful when bringing the values of the variables in. The sign and the unit are essential to write. Here we have positive 60 microns per second, positive 20 microns per second, positive 5 microns per second squared, and negative 2 microns per second squared. Alright, now let's calculate the numbers and the units. So delta t is 80 divided by 7 seconds, approximately 11.428 seconds. Now we can take this delta t and plug it back into any other equations of motion we had earlier to calculate delta x. Again, pay extra attention to sign and unit, and make sure you write them down to keep track of your calculation. Delta x is 27,200 divided by 44 microns, approximately 555.102 microns. For part B, we want to have x versus t and to be as accurate as possible. We always keep the x-axis vertical and assume you have the unit, microns here, written by the axis label. The t-axis is in second. Let's approximately mark the final position, which is around 555 microns, and a bit over 11 seconds. Again, I want to write down the given values of the problem. As we know, for bacteria 1, the initial velocity and acceleration are positive. So I'm expecting the B1 curve to look like a smiley face or a portion of it. The velocity of bacteria 2 is positive while its acceleration is negative. So I'm expecting a curve like a sad face or a portion of it. Now the question is when the turning point for bacteria 2 happens. Let me rephrase this. I want to see the turning point for bacteria 2 is between 0 to 11 seconds or after. Because if it is between 0 to 11 seconds, I need to mark it in the plot. To find bacteria 2 turning point, I use the velocity acceleration equation. The initial time is 0, and the only thing we don't have, and actually we are looking for it, is the final time, also known as turning point time in this case. For the left-hand side of the equation, we know at the turning point, speed is 0. We have the initial velocity as positive 60 microns per second. So we see that the delta V for bacteria 2 from the initial point to the turning point is negative 60 microns per second. On the right hand side, we know the acceleration of bacteria 2 is negative 2. After plugging the values, we find that turning point happens at delta t equal 30 seconds, which is way past 11 seconds. Good, we don't need to worry about it then. Now let's sketch the curves. The initial velocity of bacteria 2 is 3 times larger than bacteria 1. So the slope of the plot at time 0 of bacteria 2 in red needs to be 3 times larger than the slope of curve for bacteria 1 in blue. Now let's sketch a sad phase for bacteria 2, and a happy phase for bacteria 1. And make sure they meet at a bit after 11 seconds along the horizontal axis and 555 microns along the vertical axis. Alright, that was all for this problem. If you like to work through more sample problems, please check our website, PhysAcademy.com.